Hello, in this section, we will try to focus only on practicing graphing a function. And let's solve this example. Let's sketch this graph. Sketch the graph of the function that satisfied all of the given conditions. And we are asked to clearly indicate significant points on the graph, like inflection point, local minimum, local maximum, an asymptote, a vertical, horizontal, all of these type of points. Okay, let's start. We have lots of information and I believe we can get the graph. First of all, we see f of x is continuous on entire number line from negative infinity to positive infinity for all of the real numbers. Okay, this indicates that function is defined for all of the numbers and most likely, no, not most likely, definitely we do not have vertical asymptotes because all of the numbers are domain and we have continuity. Because even if function is defined everywhere, we can still have a vertical asymptote, but then we will have some gaps, some infinite discontinuity. But no vertical asymptotes, function is nice and smooth and continuous. F at 0 is free. That's actually x-intercept. Okay? This is because the value for 0 is free. Not x, that's the y-intercept because x is 0. Okay, that's the y-intercept. Okay. Too many. Now, limit at positive infinity is 2. And that means the behavior at positive infinity is 2. Function is approaching the line 2, and this is horizontal asymptote. At negative infinity, all of the values are approaching 0. At negative infinity, horizontal asymptote is 0. And I do have next slide dedicated for the graph, but let's try to squeeze here. I can draw horizontal asymptote 2 and horizontal asymptote 0. Okay, one is at positive, one is at negative infinity. We are allowed to intersect these asymptotes, but not at infinity. Okay? We have to respect, function must respect the asymptote, the horizontal asymptote. And how we will reach to that point because we need to know concavity, but I can maybe mention now, and we will try to remember, if function is concave up at positive infinity, okay, then and having a horizontal asymptote, we will always end up with the graph being placed above the above the asymptote, okay? Because we can see it's gently, but it is bended, it is concave up. If we will end up that our function is actually concave down at positive infinity, respecting an asymptote, we will draw a function below the asymptote, because then we can't intersect. Okay? And the same thing we will apply on the negative. Yeah? Concave up, above the horizontal asymptote, concave down, below. Okay, now the next line is telling us that derivative is 0 at -3 and 5. We may think that that's the critical points, because if the derivative is 0, we will have local maximum, local minimum. Yeah, I can say critical numbers. Okay, now first derivative is positive on these intervals, then function is increasing. Function is increasing from negative infinity to -3, and then from 5 to positive infinity. And between -3 and 5, function is decreasing because the first derivative is negative. Now, second derivative. Second derivative is 0 at -4, 2, and 7. That's the potential inflection points. But we have to check if the second derivative is changing the sign at these points. Second derivative positive, from negative infinity to -4, and then from 2 to 7, and between -4 and 2 is negative, and after 7 is also negative, then definitely all of these points are the inflection points. I can actually, let's put this on the other side, because we may like to see the test, first derivative test and concavity test, because the first derivative test will tell us that -3 and 5 are the inflection. No, the critical points. And first derivative, like we were always doing, is positive here, negative here. Then function is increasing, decreasing, increasing. Yeah, I think that's much, much better. Local minimum is happening at 5, local maximum is happening at -3. And let's test the second derivative, -4, 2 and 7. Second derivative is positive here, negative here, negative here. And then function is concave up, concave down, concave up, concave down. All of them will give us inflection point. At -4, at 2, at 7 is inflection point. We don't really see the graph at the moment, but we have to combine. Yeah? We can kind of see that the graph will be something like this. Okay, but we have to respect, and we can see function is concave. Oh, no, I don't know concavity from this. Oh, no, I don't know concavity, because at 7 we're changing the concavity. Yeah, but this function will kind of look like this, but we still have to add the inflection points. Let's use that graph and let's put the graph together. Y and X. And now this is horizontal asymptote, this is horizontal asymptote. One is at negative infinity, one is at positive infinity. At -3, we will have local maximum. Yeah, we can see local maximum, but I don't know where, here, I don't know. Let's wait. And at 5, at 5 is a local minimum. At 5 is a local minimum. This is 5, and the same, I don't know, could be everywhere, I don't want to write this actually as an asymptote. I'm just thinking that that's the points. We can figure out where is that minimum. We also have y-intercept, do we remember? 3. Okay, an inflection point at -4 and inflection point at what was the inflection point? At 2, I believe. No, let's check. Yes, 2 and 7. 2 and 7. Oh, 7. Let's see. X and 7. Okay, one thing, do you remember what we can check? We can check concavity at the endpoints. At positive infinity, looks like function is concave down. Then we have to end up, where am I? Function is concave down, then we will end up, and that's the inflection, we will end up below an asymptote. Yeah, it's just because we have to respect the asymptote. Function is approaching. If this will be concave up, then it will be not good. It will intersect. It has to be below if it's concave down. Right? That's that we will have that part of the function is here. Also, at negative infinity, function is concave up. Then we will keep our function above the asymptote. Yeah? Because we cannot keep below. Below will intersect. We cannot intersect the asymptote at infinities. Okay, so we have this. And now, at -4, actually, that's good. At -4, we will change concavity. Okay, local maximum, but I have to go here. We can always adjust, yeah? That's what you will do on your homework. Or let's do like this. Inflection point, okay. local maximum. We don't know exactly where it is. Maybe I can change a little bit because we can see inflection point, local maximum, still concave down. I'm trying to satisfy this y-intercept. And then we have another inflection point. Oh no, at 2, correct? I can show you what we can do. We will, oh, I don't know if that's correct, but what I was thinking to do, at 2, could be anywhere, yes, I can even go and change the concavity here. It's still concave down and then concave up, local maximum, and it's increasing and we're changing concavity at 7, inflection point. Local minimum value, looks like local minimum. Okay, inflection point. So we have inflection point at -4, inflection point at 2, and inflection point at x equals to 7. Okay, looks kind of, yeah, we can see, let's come back and you see the green, of course, the green graph wasn't exactly, I mean, has the same shape, almost, we didn't include the concavity. But yes, that's the nice graph of this. We're respecting the asymptotes, we have inflection points, we have y-intercept, we have local maximum, local minimum. We don't know exactly how high, like what is exactly the local maximum, for instance. Yeah, could be even higher. We don't have this information, but definitely at -3 is local maximum, at x equals to 5 is local minimum, and respectively the other inflection points. Okay, that's the graphic. And I have another one, but you can try to do it. Okay, that's exercise for you. Or you can pick the question on the homework assignment. It's also nice and quick question. But before I finish this session, I wanted to do, I think we did this question. Yes, we remember we did during the class. Let's look at this one. If we can pick which graph is correct. So now we don't have to graph it, but we can at least pick the graph. Okay, what we see, we know that limit at -infinity is positive infinity. This indicates that as x goes in the negative direction, value of the function goes up. This is good, this is good, this is good. That's not good, that's not good, because this D and E option, function goes to -infinity and we have positive infinity. Okay, as x goes to positive infinity, that's limited positive infinity, value are approaching 1. This is horizontal asymptote. Horizontal asymptote 1. Unfortunately, option A, B, and C has the horizontal asymptote and is respecting. We may quickly remove maybe one of those, or maybe 2 of those, if we will check concavity at positive infinity. Function is concave up. This one is concave down. Let's check. Function is what we have. Second derivative is negative. Then function is concave down between -infinity and 0. -infinity and 0, that's correct, that's correct, that's correct. And between 0 and 1, concave down. 0 and 1, that's not good. Yeah. And 0 and 1, because we are assuming that this is 1. Function must be concave down. That's concave up. That's not good. Okay, at least I removed this one. And now I think we can also, looking at just the concavity, we can remove, because again, I still didn't investigate concave up, concave down. But since we can see again, concave down, second derivative negative, it's only, I can draw it maybe the blue color. between negative infinity and 0, and between 0 and 1 only. Yes, only. Then we also have concave down here, but that's not a part of our conditions. A is not satisfying this, but B, yes, concave down here and here only. Any other part of the function, they have to be concave up, and they are. B is the good answer. Yeah, that we can see, that's what we did in the class, and this example, that's how we can investigate. That's how we can investigate the condition and the graph. Maybe one more and we will finish. But I would like to pick something. This one is also good. Maybe let's do this one. Formula, because then we have formulas, okay? Or maybe this one is too easy. Do you see why? We may think about the x-intercept, domain, and vertical asymptotes. We can see right away, looking at the formula of the function, denominator is never 0. Domain are all of the real numbers. We do not have any vertical asymptotes. And the x-intercept is equal to 0 because x-intercept we're computing when y is 0. Y is 0 if this fraction is 0, this fraction is 0 if the numerator is 0. For x is 0 if x is 0. That means this is good, this is good, this is good, this is good. All of them actually has the x-intercept 0, but not all of them has domain, all of the numbers. We do not have vertical asymptotes. Only C or D is the option. Okay, only C or D. And we have a big difference. We may focus, maybe this time, we can still focus on concavity, but we did the previous one on concavity. We can definitely focus on local max, local min. Yeah, this is local minimum, and that's the other way. At -1, we have local minimum. At +1, we have local maximum. We will do the first derivative test and will tell us everything. Okay, let's put the numbers. Derivative is 0 if numerator is 0. Numerator is 0 if x is -1 or +1. Yeah? Denominator is never 0, then derivative is always defined. Okay, let's test it. Let's test the sign. If I substitute 2 squared is 4, minus 1 minus 4 is negative. When we substitute 0, 1 minus 0 is positive, times 4, and -2, for instance, squared is positive, 4, 1 minus 4 is again negative. Then function is decreasing, increasing, decreasing. Okay, I mean, it looks like local minimum at -1, local maximum, decreasing, local minimum, increasing, local maximum, decreasing. And we don't even have to check the concavity because definitely function D will satisfy this. Okay, and I have more examples. You can check the slides of this graphing section. And yeah, try to eliminate some functions based on the conditions provided or based on the formula. Okay, thank you.